So you can use this slide as a guide and the facts about these atoms as a guide to knowing whether or not your Lewis structure is drawn correctly or if a group of Lewis structures are drawn correctly. So here's how I think of it. If I see a Lewis structure containing carbon and the carbon does not have 4 bonds to it, then that Lewis structure is incorrect. If the carbon has a neutral charge and it does not have 4 bonds to it, that Lewis structure is incorrect. You have to recognize these patterns just on sight. When you see carbon, you think 4 bonds. Okay? Now, nitrogen, whenever I have a molecule that has nitrogen, I know that a neutral nitrogen has to have 3 bonds and 1 lone pair. And so all of these trends that we see for each of these atoms, if you have a Lewis structure where oxygen is a neutral atom, that oxygen has to have 2 bonds and 2 lone pairs. Otherwise, the Lewis structure is incorrect. For the halides, a correct Lewis structure of a neutral halide should have 1 bond and 3 lone pairs. And never, ever, ever should hydrogen have more than 1 bond. So let's analyze these Lewis structures and identify why they are correct. I'm trying to get the pen to work. And let's go with the green. All right. So I'm going to look at each of the carbons first. And I know that in each of these Lewis structures, anytime there is a carbon, that carbon should have 4 bonds. So in Lewis structure A, carbon has 4 bonds and 0 lone pairs. So let's make a little table. Okay. So atom, carbon, let's see. Then bonds and pairs. Okay, so carbon. In Lewis structure A, there are 4 bonds and 0 pairs. In structure B, we can count each individual. Let's see. So 1, 2, 3, 4 bonds, no pairs. 1, 2, 3, 4 bonds, no pairs. So 2 single bonds, 1 double bond, that's a total of 4, no lone pairs. 1, 2, 3, 4, 4 bonds and no lone pairs. For nitrogen, I should have 3 bonds and 1 lone pair. Now we can look at each individual structure that has nitrogen. Circle all the nitrogens, and then count the number of bonds and lone pairs. This nitrogen, 1 bond to carbon, 2 bonds to hydrogen, that makes 3, and 1 lone pair. For N2, nitrogen has a triple bond to the other nitrogen, so both of those nitrogens have 3 bonds, and each of them also has 1 lone pair. So nitrogen is correct in these Lewis structures. Then we can look at oxygen. Oxygen we would expect to have 2 bonds and 2 pairs. So is that what we see? I'm going to erase some of this. So for our oxygens in these 2 Lewis structures, the first oxygen, we have 1 bonded carbon, another bonded carbon, so that's 2 bonds and 2 lone pairs. That's correct. In this molecule, which we call a carboxylic acid, we have an oxygen that has a double bond, so that's 2 bonds and 2 pairs, and the other oxygen has 1 bond to hydrogen, 1 bond to carbon, so that's 2 bonds and 2 pairs. Finally, when we draw halides, bromine, we should have 1 bond and 3 pairs. So we have number of bonds is, when we look at the structure, this bromine has 1 bond and 3 pairs. As long as we know our trends, our Lewis structures will always be drawn correctly. All right. Now, if you want the more traditional rules for drawing Lewis structures, we can also look at that. How to draw Lewis structures by the rules. The first step we always look at is determining the total number of valence electrons. So for nitrate, we have nitrogen with a valence of 5, 3 oxygens, each with a valence of 6, and a negative charge, which means we have to add 1 electron. So we have 5 plus 3 times 6 plus 1, which gives us 24 electrons. Now we have to consider how they are bonded together. The first atom written here, with the one which there is only one of, is nitrogen, and nitrogen should be made the central atom. Anytime you have a polyatomic ion with oxygen, oxygen is the outer atom and the other atom is the central atom. So for nitrate, nitrogen will be the central atom. Now, if we first draw the central atom and then draw a single bond to each of the outer atoms. So we would draw nitrogen and then 3 bonds from nitrogen each to oxygen. But when we look at that structure, we have to consider after you fill in the bonds to the outer atoms, then you fill in the lone pairs. So you fill in lone pairs until each of the outer atoms has an octet. And then if there are any electrons remaining, you put them on the central atom until it has an octet. When we draw nitrate, when we get to the central atom nitrogen, and we've drawn all of our electrons and all of our bonds, we don't have any electrons left to give the central atom an octet. Once you've done this step, you have to reevaluate. If the central atom is left without an octet, following the rules of central atom, 1, 2 bonds to outer atom, 3 lone pairs to outer atoms until all have octet. And then 4 remaining electrons on a central atom. If the central atom does not have an octet, then you have to remove lone pairs from outer atoms to make a multiple bond. So that is what was done with nitrate. We got to the structure at the left, and the nitrogen did not have a complete octet. Then a lone pair was taken from an outer atom and moved into a multiple bond. That gave us a nitrogen with 2 single bonds to oxygen and 1 double bond to oxygen. From there, the Lewis structure is not complete until the formal charge of all atoms is assessed. If the formal charge is 0, then you don't have to write anything, but if the formal charge is not 0, you must write what the formal charge is. Now this is when we draw Lewis structures, you have to write the formal charge. And so whenever nitrogen doesn't have 3 bonds and 1 lone pair, it's going to have a charge. In this case, nitrogen has 4 bonds. When nitrogen has 4 bonds, it has a positive charge. You can do the rule for formal charge if you want, which is valence 5 minus number of bonds 4 minus number of dots, which is 0, and you'll see that nitrogen has a positive 1 charge. For myself, I just remember that when nitrogen has 4 bonds, it's positive. When nitrogen has 3 bonds and 1 lone pair, it's 0. And when nitrogen has 2 bonds, it's negative 1. Well, 2 bonds and 2 pairs, it's negative 1. Whenever oxygen is 2 bonds and 2 pairs, I know that the charge is 0. So the double bonded oxygen I can leave alone. When oxygen has 3 lone pairs and 1 bond, it will be negatively charged. And we can prove that using the formula for calculating formal charge. A valence of 6 minus 1 bond minus 6 dots is equal to negative 1. Therefore, both of the single bonded oxygens that have 3 pairs must have a negative charge. The overall charge of nitrate is negative 1 because of the positive charge on nitrogen is canceled by one of the negative charges on oxygen, so that only one of the negative charges counts. In organic chemistry, the most common structures we use are Kekulé structures, condensed structures, and skeletal structures. When we draw these structures, for Kekulé structures, we do not draw lone pairs. But you must remember that they are present. Also, in condensed structures, We do not draw bonds. Or lone pairs. But the connectivity is shown by the order in which the atoms are written. So these Kekulé structures are almost identical to Lewis structures, except that lone pairs are not shown. The condensed structures, lone pairs and bonds are not shown. We can compare the two. Look at the Kekulé structure of the first molecule, carbon bonded to bromine and 3 hydrogens. The order in which the atoms are written indicates how the condensed structure will be written. Carbon is bonded to 3 hydrogens, CH3, and then bonded to 1 heteroatom, bromine. That's an interesting word, heteroatom. It's a name that is going to come up very often in this class. What is a heteroatom? A heteroatom, hetero meaning different, spelling. Hetero equals different. Since organic chemistry is all about carbon and hydrogen, anything that is not carbon or hydrogen is a heteroatom. Therefore, bromine, oxygen, and nitrogen are all heteroatoms. The heteroatoms that are bonded to carbon, which is also bonded to hydrogen, will always be written after hydrogen. So let me write that down. Okay. The heteroatom is always written after hydrogens bonded to same carbon. Okay. Please be careful when you draw your structures to make sure that they are valid. Carbon should have 4 bonds, oxygen should have 2 bonds, hydrogens should have 1 bond. In the case of the second molecule in the Kekulé structures, we have CH3, C, and 3 hydrogens bonded to 1 oxygen. That oxygen is then bonded to carbon, as shown above, and then the carbon is bonded to 3 hydrogens. 1, 2, 3. The next molecule, formic acid, is written CO2H. This is a functional group. This is an abbreviation for a functional group, CO2H. You should remember the way in which this is written and what structure it corresponds to. This is a carbon that is bonded to a hydrogen, which is also bonded to 2 oxygens. And then the final hydrogen is bonded to 1 of the 2 oxygens. So if you see the structure above, we have this hydrogen here bonded to carbon. the carbon is bonded to two oxygens. Those oxygens are not bonded to each other, they are both bonded to the carbon. So this carbon then, for one of the two oxygens, is carbon double bonded to oxygen, and the other oxygen must be in a single bond to the carbon, because this depicts that only 3 atoms are bonded to the carbon, 1 hydrogen and 2 oxygens. But carbon must have a total of 4 bonds. That means that if only 3 atoms are bonded to the carbon, one of the 3 atoms must have a double bond to carbon to add up to 4 bonds. So we have a total of 1, 2, 3, 4 bonds to carbon by giving one of the 3 atoms bonded to carbon a double bond. This also satisfies the oxygen, which must have 2 bonds. The oxygen, which is single bonded to carbon, will then be bonded to the hydrogen that is written last. Then we have methylamine, the last molecule, well, second to last molecule, but we've looked at N2 before. We have a carbon bonded to 3 hydrogens and then a nitrogen. So carbon bonded to 3 hydrogens, followed by a bond to nitrogen. This nitrogen is bonded to 2 hydrogens. Following our rules, carbon should have 4 bonds, and it does. It turned off my laser pointer. Okay, carbon should have 4 bonds, and the nitrogen should have 3 bonds, and they do. And so this is the correct Lewis structure. Finally, when we draw N2, they must be nitrogen bonded to each other. And in N2, those nitrogens are in a triple bond, so that each nitrogen has 3 bonds. And I'm going to give you an assignment to do where you are going to practice drawing these structures.